Hey guys, I was totally surprised. The clock on my desktop is late. All right, you know what? It's already 1:20. And good afternoon to you all. Now that includes also Eric, Kenny, Ding Xuan, Ricky, Louis, Pinyu, Bingwei, Gao Pu, and yeah, the new theme song, because I can feel that the spring is probably gone and the summer is probably coming. All right, and guys, welcome back to Introduction to Computer Networks at NTU. And this is week 12, episode 21. And this week, congrats. So we have only 3 quizzes due, and all of them are somewhat straightforward. 36 might be a little bit open-ended, but it shouldn't be challenging. Okay. And with that said, I would like to draw your attention to the schedule for the semester. So this is the course page. If you click into the schedule link, week 12 is right here. And this is to let you know that we have only 4 weeks of lectures remaining. Okay, so just hang there. Summer is close. Okay, the summer break is near. All right, and by the way, you guys did really well with the exam too. These PA-related problems were challenging. The students from previous years don't get to complete these PA-related problems so well. So I'm gonna have trouble this semester giving grades. Okay, so guys, don't be surprised that even though your exam grades are high, participation high, but I might still need to somehow align you guys such that I lay the average somewhere to a number that the university is expecting. Okay, so guys, essentially what I'm trying to say is that it's not me deciding how well the grades you receive. It's more that you're compared to others. Okay, so I'm gonna sort you guys, and the average is gonna fall somewhere as instructed by the university, because the grade inflation thing is an issue now. Okay, guys, so be mentally prepared. All right, now let's move on to the topics today. All right. Last week we started introducing chapter 4 already, and by talking about the components inside the router, because chapter 4, chapter 5 are the network layer, and the network layer devices are signaturely the routers. And we introduced there are 4 major components. There's a switching fabric that is supposed to run really, really fast in nanoseconds, because forwarding is like for every packet, and there's so many packets to go through. So this forwarding function is go really, really fast. And then there's this logic controller that's doing the route computation. And route computation is something that you calculate ahead of the time of travel, ahead of the time that we need to forward packets. Okay? And it will be something that's more intelligent. There's more computation power, but it doesn't need to run like every second, nanosecond. Usually it runs like every now and then when the routes change. And then we have 2 very important components called the incoming queue and the incoming ports and outgoing ports. And we started introducing this function, forwarding, and how it works in the incoming ports, right? And it's essentially doing what? IP address table lookup. So you have a forwarding table, there's a bunch of IP addresses. And for each IP address, there's an outgoing interface. So to find out what the outgoing interface is for a packet is just to look up, to find a match in the table. And so quiz 33 and 34 are for you to find, to simulate how the forwarding function works by looking up table and find the outgoing port. And another thing is this, if we list all the possible IP addresses in the table, then you have a super long table. Not only that it's going to be slow looking up such a table, but also, it's going to cost a lot of money to create so much memory space to just keep that table, right? So we tend to aggregate the IP addresses okay, by the prefix. And therefore, the forwarding function is doing what? The longest prefix lookup or longest prefix matching. Okay. So you see that it's very important to make sure that forwarding goes really fast. And today, the topics, the first part of today, the topics will still be related to the router. We'll talk a little bit more about each of the components. The first topic is called TCAM. This is related to how we do fast lookup. So TCAM is a special hardware. It's a memory, a kind of memory. It's so that we can optimize the lookup process and ensure that when a packet arrives, the outgoing interface lookup will be done in one cycle. All right. The only drawback of using TCAM is that it's expensive.
Longest prefix matching is really nice because you see in the forwarding table, there are so many less entries, right, as opposed to 2 to the power of 32. So memory requirement at the input port, less. Lookup process, faster because, again, less entries to look for. So less memory, faster lookup, 2 benefits. There's one more benefit that justifies why we use longest prefix matching, but we'll talk about that later in section 4.3, IP addressing. Now back to longest prefix matching. If you recall, we say in the lower part of the router, the data plane, what we do is to often use hardware to optimize all sorts of processing there. Longest prefix matching is performed this way, also using a specialized hardware called the TCAMs, ternary content addressable memories. Okay, the idea of this is this. It's not strictly a memory space. It's actually a memory space with some computation circuitry. So the main circuitry there is a searching interconnected network. Provided the destination address, which is a prefix, this searching network allows it to go really fast and go to an exit point where the output port is stored. Okay, so the searching circuitry is fired really quick, okay, taking the exit in 1 clock cycle. Now, the part that is a bit slow is to insert the right port number at different exit points. And that is done when the routing processor finishes computing the route, when we're installing the forwarding table. So the installation of the forwarding table there using TCAM is to install is to assign the right port number at different exit point in this searching interconnected network. And that is why when packet comes in, the searching part is really, really fast within 1 clock cycle. So the forwarding table installation is only 1 time, so it's not a big deal, okay, although longer. But for all the packets coming in, that's very, very frequent, very fast. Okay. Now, as you can imagine, TCAM is very expensive. Okay. Cisco Catalyst series there allow us to store 1 million of these prefix entries. So very expensive router. And by the way, Cisco is one of the biggest router designers, router manufacturers. There are actually a number of these router manufacturers in Taiwan as well, like D-Link, like Asus, yeah. But the routers manufactured in Taiwan are usually lower cost, okay? Good enough for maybe home use, maybe for access point use, maybe for enterprise use.
All right, now we move on to talk about switching fabric. There are 3 generations of design. You will see in the video that one is growingly faster and more advanced than the other. And the video is about 5 minutes.
The switching processing the data plane is also optimized by hardware. And that hardware is called the switching fabric. And the goal of the switching fabric is very simple, to move packets from the input port to the output port. And the key design metric is the switching rate. Now, one thing that one needs to be very careful designing a router is if we design such that there are n input ports possible, and the line speed of each input port is R, then you want to make sure that the switching fabric can switch at this rate, R multiply N. All right, so what we're seeing here are 3 different architectures of switching fabric. Memory is generation number 1, bus number 2, and the modern ones, generation 3, the crossbar architecture. Now let's go over them one by one. So first generation, switching via memory. Okay. The architecture of a router of the switching fabric is very much like a traditional computer, where we have a CPU, memory, and then hard disk. So we fetch data from the hard disk to the memory first before we fetch the data from the memory to the register, and therefore we fire the computation circuitry. Okay. So memory there is the middle point. Before data can go anywhere, you get it from the source. okay, before you push it out. So similarly here, we do have packet in the input port and we want to push it to the output port. The packet is going to be copied to the system memory here in the middle, okay, like this, through the system bus. Okay. And then from the memory, copy them to the output port's memory. So the speed of moving the packets is limited pretty much by the memory here. Okay? The speed to write and the speed to read. Now this is usually very slow and the cost of the memory is also high. And not to mention this, we send packets into the memory like this, and we also fetch packets out from the memory like this. So you see each packet has 2 bus crossings. If the bus speed is R, the throughput can only be this much advanced. If this is not limiting memory's read-write access time. Therefore, in the second architecture, that's bypass the memory entirely, so let's remove the memory part, there's no middle point. Packet is copied straight from the input port memory to the output port memory, like this. Okay. And as a result, we only have what? 1 bus crossing. That is saying, the bus rate is exactly the throughput. And this is actually in the Cisco 5600 series. Having a 32 gigabits per second bus guarantees also 32 gigabits per second switching rate. Now the only limitation is just the bus. Okay, there could be bus contention depending on how many input ports you have and how busy they are. Last architecture is this interconnection network or the crossbar network. The architecture looks like this. So the input ports are connected to a network, and then output ports are exit points of the network. So you see potentially this. Yeah, these red lines are buses. Okay, bus speed can still be R. All right, but you know what? Data can potentially flow here, this pass. So you get 3 flows that can potentially go through the interconnect network in parallel. Although the bus speed is R, but you get triple amount of data through. Okay, so there's a certain degree of parallelism there we could explore. Okay, so this design here, the crossbar design, or sometimes called the grid design. Okay, it could be 2-dimensional grid, but nowadays 3-dimensional grids is also quite common. Okay, so we use an interconnected network there to try to speed up, add some degree of parallelism. Now this design is actually not new. When people are designing computers where there are multiple processors, the multiprocessor computers, people have already thought about using this architecture to ensure the processors are well connected so that we could distribute computation tasks efficiently. We allow fast passing of the data from one processor to another so they can continue the computation from another computer, okay, another processor. Right? The last part of doing interconnected network architecture is this. We'll have to cut the bigger data gram into smaller cells, okay, and fixed size cell. It's very important it's fixed size. So yeah, the transmission of these cells is very fine-grained and easy to control because it's fixed. The time, duration, very stable, very fixed. So that avoids also contention on such an interconnection network. And therefore, Cisco 12000 is one such switching fabric-based router. It can switch about twice, okay, amount of data than the bus-based switch fabric.
All right, good. So there's a pop-up quiz on the live chat. Polly asked you guys to sort these 3 types of switching fabrics from the fastest to the slowest. Okay, so if you pay attention to the video, it should be easy. All right, very good, guys. And the next topic is called buffer management, because router is where we buffer packets, and there are actually multiple places in a router we buffer packets. Very good, very good. So buffer management is a huge topic. Okay, so in this coming video, you will hear Polly give a very high-level overview of buffer management and introduce a problem called head-of-line blocking. It's a very special problem that happens in between the incoming ports, the switching fabric, and the outgoing ports. Okay, and it happens only to the output port contention type of router. It's a little bit special, but it's good to know. You will see sometimes packets, it's actually free for the packet to go, but it gets blocked by someone else who's not free to go. All right, so head-of-line blocking.
There's one very important mechanism needs to be implemented in a router. That's called the buffer management. we'll need it in the input port as well as output port. Now, the reason that we need it in the input port is this: when the switching fabric is slower than the input port rates combined, packets coming in really, really fast, then these packets might need to be queued temporarily at the buffer. That's why we see queuing delay. When the buffer is full, packet get dropped. So the queuing strategy and the dropping policy, as well as how much buffer we should allocate to this input port, those things are all part of the buffer management, which we'll talk more about in the next few slides. Before that, let's talk about this very special kind of queuing delay. It's called the HOL blocking. Now let's focus on the scenario. It's easier to understand that way. So this router here I'm illustrating has output port contention. So this is one special type of router. What it means there is each output port can only draw in one packet at a time. So this red port here is only taking in red packet, and it can only take in one red packet at a time. Similarly, for the blue port, taking in blue packets. Green port taking in green packets. Now, the input ports, there are 3 of them. Input port number 1 here has a red packet at the front. Input port 3 here also has a red packet at the front. Now, this is what? An output port contention based router. So we can only pick one of these to accept into the output port. Let's assume this one goes through and this one gets blocked. One packet time later, you see this red packet arriving at the output port. That's why we see the red packet here. This blue packet arrives at the blue port. That's why we see the blue packet here. But this one stays. Therefore, one packet time later, this red packet stays. But if you consider this case where the green packet's at the front and the red packet's in the back, then we could have what? One packet time later, the red packet, blue packet, as well as the green packets, all 3 of them move to the output port. So instead of receiving only 2, we could have 3 packets through. Isn't that better? Yes. So green packet in this scenario here, it gets blocked unnecessarily when they can really be moving forward. So that is called the head of line blocking. Green packet here experiencing a head of line blocking, head of line queuing, because other packets such as the green one is blocked by the red packet at the front. And somehow the output port is not accepting multiple packets coming in at a time. On the other hand, if you have a router that implements the non-output port contention mechanism, then we could have what? Input port 1, input port 3, both have red packets. They can now all go to the red output port. So one packet time later, you see 2 of them here. And the blue one will also go one packet time later. And the next cycle, then you see green, the next one in line in input port 1 goes to the green port. And the red packet here goes to the red port. So HOL blocking only occur in the output port contention type of router. So that was the divergence. Speaking of this very special type of queuing one might experience. Now let's come back to buffer management. We need also buffer management at the output port. And this is because the arrival rate through the fabric could exceed the output line speed. So switch here super fast, such as a non-output port contention router. Usually the packet can come in real quick. We could have red, red, red here, then all of a sudden we get 3 red packets coming in. And if the line speed here is slow, the buffer actually queued up real quick. It gets full real quick. So delay also gets long, and you might also have packet loss. And the buffer here also needs to be managed.
All right, good. And next video, a little bit shorter than 2 minutes, is the formal introduction of buffer management. This is a very important function in a router.
Buffer management in the input port and output ports are the same, so let's just talk about the output port side. So what I'm drawing here is the detail of the output port. So it looks very much like the input port, except it's being mirrored. So we do have this one here. This is where the buffer space is, and packet get queued up here. And this component is doing the link layer protocol. And therefore this one here, although called line termination, but this is where also the physical layer is implemented. Now let's focus on buffer management here. So buffering is required because data could be coming in faster than the pace they'll be going out. So when that occurs, we could draw packets when there's not enough buffer space. So what's critical here is to decide how much space to allocate to the buffer. And in case we need to drop a packet, do we always drop the incoming one, or maybe we pick one of those packets existing here? Okay, because that seems to be a bit fair, right? Because the packets get queued up here could be coming from one flow. So the later flow, if we drop, from within the queue, then it will be more fair to the later traffic. Second issue is this. Yeah, so the packets will be drawn out of the queue and get onto the outgoing link. Which one do we pick? Okay, one could actually start from the first one, but one can also pick one of the packets seems to be more important and pass it out further. So, yeah, perhaps you could have some sort of priority-based mechanism so that the packets can be classified and some go out earlier than the others. Or we might want to maintain that it's fair, okay? So we want to maintain neutral so that treatment of all these packets will equal.
All right, good. So first video here talks a little bit more about the buffering mechanism, in that we decide how big the buffer space is, and when the packet arrives, do we drop it or keep it? If we keep it, where in the buffer we keep it? That's called buffering.
And the first part of the buffer management is this, determining how much space being allocated to the buffer. Yeah, the documentation says this, the buffer space should equal to the typical round trip time multiplying the capacity. Yeah, the intuition behind this is this. It has something to do with how TCP does the condition control. You see, in TCP, data being sent, X coming back. After receiving duplicate X or waiting for timeout, then the source will discover there's a packet loss, there's a condition, and therefore slow down. All right? So router in the middle there, okay, is thinking, well, I'll need to buffer the packets long enough before the sources know they need to slow down, right? And that is at least one round trip time. And during this amount of time, there could be this much packet or this much data going through the link here. So that's why RTT multiplying the capacity here. In this example, we have the round trip time 250 milliseconds and the capacity being 10 gigabits. These are very typical values, but you see also, the amount of memory requirement pretty high, 2.5 gigabits. So not exactly practical. So some of the recent study actually discovered this. If all these flows going through the routers are TCP flows, okay, and if there are n of them, we could actually reduce the buffer requirement to this amount. Still, RTT multiplying C at the top, but we can actually divide it by a certain factor. The more TCP flows there are, the more we could reduce the buffer space requirement. Okay. So N here are TCP flows, N flows here are N TCP flows. The reason for this is twofold. One being, hey, TCP at the beginning is doing slow start, starting from window size 1. And the sending rate is very, very slow. Okay? And there are a lot of data we send over the internet being very, very small, and so we use a very slow rate to send small data. Okay? So most of these TCP flows run in the low rate. Okay, so we are actually not using the entire C capacity. Second is this. Even though we are in the steady state, okay, these window sizes are all pushing and dropping, okay, chances also high that we are not using the full capacity as well. Okay, so still also low, but not as low. Okay, in the slow start state, sending rate really low. Even in the congestion avoidance rate, it's actually lower than the capacity as well. Okay, so that's why we come up with the factor here. The second component in the buffer management is this, the dropping policy or the discard policy. So this is needed when packet arrives to a full queue, right? So, hey, either the arriving packet needs to be dropped or one of the packets in the queue needs to be dropped. Okay, so generally, pick the next packet to discard. Okay. The most common policy is this, tail drop. So this is essentially just to drop the packet that is coming in the last, okay? Because usually those who arrive early are given priority. But you could actually change that, okay? Assign priority to the packets. Some of the packets might be less important, right? So we could classify them to lower priority. When a packet comes in with a higher priority, then we drop one with a lower priority. Third, random. Of course, one could pick randomly from the queue a packet being discarded, right?
All right, so buffering. Next is scheduling. When these packets get a space on the link to go out, which packet do we select? Do we schedule next? So this is called scheduling.
The last component is this. Yeah, how do we debuffer? Okay, which packet do we choose to transmit next? Okay, so the next packet to send on the link. This is also called the scheduling policy. Typically, we do this FIFO. Okay, first in, first out. So essentially, based on the packet, based on the order the packet arrives, we take one out at a time. But okay, one can also do this, the class-based scheduling. Okay, the way to do it is to divide the packets also based on the priority or based on the classes. Okay, and so we could assign a specific class being higher priority versus others. Or we could have them rotating turns, taking one packet from each class at a time. And we can actually allow multiple packets coming from one class at a time, and so that there are more packets coming out from a particular class. It's sort of a combination. So weighted fair queuing here, WFQ, is a combination of the priority and round robin. Let's go into each one of these a little bit more. So priority-based scheduling. So we send always the highest priority packet out. Okay, so when there are multiple classes, okay, with different priorities, so we send out the one always with the higher priority. If there are no packets existing, then we take whatever we have. Right? So here's an example. Packet arriving, some being red and some being green. Green packets are the one with the lower priority, while the red ones are the one with the higher priority. Okay. So the way it works is going to follow this timeline here. So a packet is arriving at this particular time. And so there'll be some time it takes for the packet to be served. And then after they finish serving, packet exit. So yeah, let's say packet 1 arrives here. All right, so right there, packet number 1 being served. And it's going to take some time here. At this point, packet 1 will exit. But there could be other packet arriving while we're serving packet 1. So 2 and 3 arrives here. But 2 is carrying a lower priority, while 3 here carrying a higher priority. So in priority scheduling, which of these 2 versus 3, will be scheduled next here? Always the one with the higher priority, which means 3 here, right? And then next 2. Now, while we serve packet 2, if packet 4 arrives, yeah, right after packet 2 exit, we enter and serve 4, and so on and so forth. Now, if we do round robin, okay, the rotation-based, class-based queuing, we do have multiple classes, but we do the cyclical scan, okay, of different class queues and send one at a time. So the same pattern, 1, 2, 3, 4, 5 packet arriving at these point in time. Okay. But this time, okay, the second packet is higher priority, third packet lower priority. So which one do we send next? We actually send packet 3 because it belongs to the other class. Not necessarily lower class, but the other class, we have to rotate. Therefore, after red packet is served, we serve the green packet. Now, because the next rotation is red packet again, so we take packet 2. Okay. Now, the next one should be green again because there's no green packet at all, so we serve packet 4, and so on and so forth. Last is the combination of priority and round robin, so weighted fair queuing here. Okay. So this is a generalized round robin. And it's almost like having some level of priority here. You assign weights to different queue. So weight number 1, weight number 2, and weight number 3 here. Okay, so in one round, we could draw 2 packets out of the red queue, and 1 packet out of the green queue, and 3 packets out of the blue queue. Okay. In the second round, 2 more, 1 more, and 3 more, but because there's only 1 left, so we just get 1 more out. So this is weighted fair queuing.
Yeah, so there's a pop-up quiz, number 2. What scheduling policy does Family Mart cashier implement? Okay, I mean normally, okay, generally speaking. Yeah, I see that all of you say FIFO, first in, first out, right? Good. Generally, that's the case. I've seen once that someone met, one of the cashiers saw her friends waiting in the line and then started another counter and received her friend first. That was not good. Okay, so scheduling. When you're waiting in a queue, who's the next to get served? All right, and so to this point, we finished introducing the components inside a router. We'll switch gear and talk about the next thing, the IPv4 protocol. Okay, so in transport layer, we talk about two protocols, UDP and TCP. These are the only two protocols on the internet in the transport layer. In the network layer, yeah, there's only one protocol, the IP protocol. And this version of IP protocol called IPv4 is a earlier version, and that has run for a long time and still existing. And the next one is IPv6, which we'll talk about tomorrow. And so just like when we introduced UDP and TCP, we introduced the packet headers, the packet format. So the first video here is you see Polly giving you a very high-level overview of what the network layer does. Okay, and then Polly pops up the IPv4 packet header, and there are so many fields. It will take some 5 minutes time to go over them. But towards the end, you will hear Polly start counting the size of the packet header. And you will hear also that, oh, the IPv4 packet header is 20 bytes long, which is the same size as the TCP packet header. So now you should have a mental picture that the IPv4 packet header is just as complex as the TCP packet header. Okay, so pay attention to this video.
4.3, Internet Protocol. Now you see here the section is a little bit long, so do expect that we spend quite a bit of time here. All right, so network layer is in the middle, okay, of the protocol stack. So what I'm showing here are, again, the important functions to be implemented there. Forwarding, we've already talked about in 4.2. Routing being in the data plane, we'll only talk about it in Chapter 5. Another thing we'll talk about in Chapter 5 is this, ICMP. This is one of those management protocols. So just like routing, management is also one of the control plane functions. So we'll be talking about ICMP later in Chapter 5. So what's left in Chapter 4 is just this, IP protocol. In there, we're going to talk about this IP addresses. If you recall, in forwarding function, the traditional model actually checks what? The destination IP address. So that's definitely talk more about the address format. Okay? And in the modern forwarding, we do what? SDN. We could actually look at multiple fields in the packet header, okay, to decide where to go. So we do need to know a little bit better about the packet format. What are the header fields? So that's coming right now. Now the two most important fields, source IP address and the destination IP address, each 32 bits long. Second, the header checksum. Now the reason this is important is because we did have what? TCP or UDP checksum that would ensure the integrity of this part of the packet. What about this part of the packet, the header part of the packet? We needed a checksum here, okay, to ensure the header part is also not having any bit errors. Now let's go over these individual fields one by one. So focus on the first row now. First field, there is called the version. So the packet we are actually showing here is defined in IP version 4. Okay, so the version number, therefore, will be 4 here, always. And then two other fields, header length and the length. So the header length here is to tell the size of the header, and the length here telling the entire packet size. Last field in the first row, the TOS. Okay. It looks a bit familiar, isn't it? Because when we're talking about congestion control, there's this flavor called the network assisted approach. So we did introduce one mechanism that requires the use of the ECM bits. So these are 2 bits in the IP packet header, if you recall. This is explicit congestion notification. So those 2 bits are right here, again, in the IP packet header. Now let's switch gear and take a look at the fields in the third row. Okay, first is here, time to live. So this field is very, very special. Okay, we've never seen it before, and it will probably make sense, only it's in the IP layer. Okay, so we would do this. We would decrement the value here, time to live, TTL, by 1, okay, after a packet passed through a router. Okay. When this value reaches 0, what we will do there, this router is going to discard the packet entirely. Okay. That is also saying a packet here, given n as the TTL, will only be able to hop n routers on the internet. okay? And afterwards, it's going to be just dropped. So time to live here is kind of regulating, okay, how many hops the packet can travel on the internet. The reason we need this is because, on the internet, routing algorithms, okay, depending on how the messages are exchanged, depending on the computation process, we sometimes ended up having loops in the routes being computed. Now, in these cases, packets can actually travel the internet forever, like ghosts. Okay, so not good to have these ghosts, all right? So let's set a time to live so that they're more human-like, right? So maximum number of hops the packet can travel. Second field in the third row, upper layer. Okay, so this is something that's slightly familiar because this is telling, okay, the network layer that after we extract the segment part, which place in the operating system we pass the segment forward. Okay, so the upper layer protocol, what is that function there? Okay, handling this incoming of a segment. Okay, so upper layer protocol to deliver the payload. It could be the UDP handler or the TCP socket handler. Now the second row. So these three fields in the second row are actually working together, okay, supporting each other. And it's for a very important functionality called the fragmentation and reassembly. The thing is that the IP datagram, when it enters the link layer, now the link layer actually defines a maximum packet size or maximum frame size. The packet in the link layer is called a frame. Okay? Now that size can very well be smaller than the IP packet size. So in that case, we need to cut a big datagram into smaller frames. Now these flags there, okay, are allowing us to reassemble the frames back so that we can recompose the original packet, original IP datagram. Last field, okay, here, the options. Now these are optional because it's usually for debugging purpose. For example, if we want to make sure that we track at which time point this packet traveled through a particular router, we could have the router adding a timestamp here. Okay. If we want to make sure that we know the exact path this packet is traveling through, now each router there in the middle can sign here so that we know exactly which router this packet has visited already. Okay. Now, if you sum the header size together, okay, so each row is 32 bits, so it's 4 by each row, and we do have how many rows? 1, 2, 3, 4, 5 minimum, right? So that's at least 20 bytes. So the IP packet header itself, 20 bytes. Now we didn't count the TCP packet header explicitly, but it's also 20 bytes. Right? So that's at least 40 bytes of header, okay, in a packet. Now if we are sending data that's very, very short, like 3 bytes, 4 bytes, the overhead, okay, of sending data with large header like this can be pretty high. Okay, so one of the problem in IPv4 is that the packet header there contains fields that might not be really necessary. So later you will see in IPv6, they will try to make it as concise as possible.
All right, so that's the packet format, the packet headers, okay, quite complex as you can see. Tomorrow we'll see how that packet header in IPv6 might be made more compact. It's not actually smaller, but definitely fewer fields, more compact. Okay. In the video, especially towards the end, there's a row of headers for fragmentation and reassembly. Okay, so the next video here, 6 minutes long, is to explain what fragmentation is and reassembly is. You will hear that the network layer, IPv4 so to speak, is a poor guy. So in case you feel that you are the poor guy in your team, does all the work, you feel for IPv4 as well. If you recall, from the transport layer to the network layer, right? The fragments, as it arrive at the network layer, it might be broken into several datagrams, and we pass the datagrams at the network layer. But you know what? From the network layer, going down to the next layer, the link layer, that datagram will also be broken into frames. But you see, it's not the link layer that are breaking the datagrams to frames. It is IPv4 again to break the datagrams into frames. So IPv4 there is the guy who does all the things. Okay, and so that fragmentation and reassembly function is to break the datagrams into fragments of frames, and at the receiver side to identify which fragments belong to the original datagram and reassemble them back. Okay, so this video also a little bit long, 6 minutes. Follow through these, and that will conclude IPv4 packet format.
So that is the IP packet format. There's one thing we're yet to talk about, the fragmentation and reassembly. Remember the second rows of the header fields. So those fields are related to this function, fragmentation and reassembly of the IP datagram. The reason we need this is this. Okay, packets, as they travel the network, they might go over different network links. So for example, packet traveling the network like this. Now this could be an Ethernet link, this could be an optical link, and this could be yet another optical link, while this is another Ethernet link. So these packets might be going through different link layer technologies, running different link layer protocols. In those protocols, they might have different MTUs being defined. So this is the maximum transfer size, essentially the maximum packet size at the link layer. So different link types, different MTUs. Some of these MTUs can be smaller than the IP datagram size. In this case, we need to break the IP datagrams into smaller parts before passing on to the link layer. Now, some of you might be thinking, wait. Hey, didn't we do something like this in the transport layer, right? We take messages from the application layer, break the message into smaller parts, add the transport layer header, and that form a segment, and we pass it down to the network layer. At the network layer, what do? We break the segment into multiple parts, add the IP header, and then pass it down to the link. So why didn't we just do that, right? Because then at the link layer can just break the datagram, right, into parts and add the frame header, and such that it's smaller than MTU. Problem solved. You're right. It's just that the link layer protocols here, okay, they are all quite primitive, and there's a good reason for that. That is because we do want packets to travel really fast on a link. Okay, so link layer protocol does not do the segmenting datagram implementation. So that's why the network layer there, okay, poor network layer. The network layer needs to break segments apart for the transport layer. The network layer also needs to break the datagram apart for the link layer. Okay, so fragmentation reassembly is actually to do the link layer's job of breaking the datagram apart and reassembling them back. Now let's see how it works. A large IP datagram needs to be divided into multiple parts. Okay, when we run into a link that defines a smaller MTU. Okay, so one datagram will become several datagrams like this. Note that these smaller ones are not frames. These smaller ones are IP datagrams. All right. So we actually break them into multiple parts before passing it on this link here. Now these datagrams will remain the way they are through the network and comes into destination. The reassembly is only done here, only at the destination. Okay. So only the final destination is doing the reassembly. Okay. Now the breaking of the original datagram to multiple parts and the reassembly of the multiple parts back to the original datagram is relying on those 3 IP header fields. Let's go over an example to showcase the 3 header fields: ID, fragmentation flag, and offset. The example says we do have a large datagram for 1,000 bytes, and we're running into a link with MTU being 1,500 bytes. So let me show you the result, okay, straight. So this large datagram is now fragmented into 3 smaller datagrams here. Okay. And so 1,500 is the maximum transfer unit size. So each, less than 1,500. You see there, the 3 smaller packets will all be carrying the same X. Yes, you're correct. So X is there. So the ID field there is used to identify which of these packets belong to the bigger, okay, datagram originally. Second field, you see the 3 are in sequence. First, second carries the flag 1. Only the last one carries the flag 0. So the one carrying the flag 0 is the ending packet, ending datagram. Now, these 2 would both be carrying 1, saying that they are actually earlier datagrams. But which one goes first and which one goes second? You can actually look at the offset, okay? Those carrying smaller offsets earlier. In fact, what the offset is saying is the position of the first byte here in the original data packet. Okay. So first byte here is the original byte 0. Okay. First byte here is the original, byte something. Okay. It's not exactly 185. It's actually 185 multiplying 8. Okay. So the offset is actually counting 8 bytes at a time. Okay. So that is a way to try to make sure the offset field is a little bit narrower. Because then, 1 byte packet, that's just not making sense. All right. So there, you get it. This is IP fragmentation and reassembly. Okay. Oh, and by the way, okay, if you multiply 185 to 8, you get 14A0. And that is because of this. Okay. There's only 14A0 data bytes in the first packet. Because, hey, IP packet header is 20 bytes. So total length being 1500, data can only be 14A0. Right? So as I mentioned, 185 is indicating the position of the first byte in the packet. But the position should be divided by the A. Okay, the original position divided by A will be the offset value. Therefore, offset multiplying by A, the original position.
All right, so now you see how the fragmentation and reassembly works. And so you see that those 3 fields in the packet header, okay, are the magics for reassembling to work. And next topic is IPv4 addressing. Unfortunately, this video is a little bit long. It's almost 8 minutes, and we have only about 3-4 minutes remaining. So what I'm gonna do is to end the course now today and start talking about IPv4 addressing tomorrow. All right, and guys, with that said, I say goodbye. I see you tomorrow because this video is just unfortunately almost 8 minutes long. And tomorrow, the first thing is to play this video, and quiz 35 is coming right up. All right, good. With that said, I say goodbye. See you tomorrow. Goodbye.